Okay, sorry about that because the appointment a little bit delayed. My previous doctor appointment. Okay, so let's start the second section, our today lecture. So what we already figure out what's the night spectrum frequency. So we are from the LPC. So we have an LPC coefficient. So this one is our source filter model. So it's our source filter model. So this one is a short-term prediction. So we generate or we produce is a night spectrum frequency. It's good for quantization. And then later on we are think about how to quantize this data, this parameter. So you can see later on we are consider different way to quantize the data here. So first one used to be maybe one. Before we quantization, we have to think about how to calculate the distortion. So the easy way is a mean square error. So mean square error, and the other one we are consider weighted mean square error. So all the other one based on spectrum distortion. So based on spectrum distortion is based on because LPC, what we say, night spectrum frequency. So once we are quantized, so we can reverse, we quantize the data, night spectrum frequency. So we can go back to the, based on the quantize, we are quantize coefficient, night spectrum frequency, and dequantize. So we are dequantize, we can get the data, the quantize night spectrum frequency. So quantize coefficient and dequantize. So maybe we can come back to the LPC coefficient. And LPC coefficient, you can come out your spectrum. You can come out the spectrum because we know LPC in frequency domain. So you have an original signal. You have an original speech signal. So you have original speech signal. So we know the signal. We know the signal speech frame. This one is your speech frame. So if we go back to the frequency domain, FFT to look at your signal behavior is more like this one. So however, if you using the LPC coefficient to look at the frequency spectrum is more like this one. So right now we try to using dequantize, using different because you try to quantization according different quantization level, and also consider maybe it's vector quantization. So you have many covector try to match your night spectrum frequency, and then according Hello 怎样？拜托我在上课，好，明天。Okay. So one issue here, we have to take care the spectrum because different coefficient we have to do dequantize. So because we have a coefficient, so different quantization level will be recover different envelope shape, because we know LPC coefficient is related to your signal envelope shape. in frequent domain is like an envelope shape. So so different quantize like during your quantize, so we can use in like a covector. So this one is a vector quantization, because this one we have a 10 element, you know. So 10 elements, so could be the covector. So we have a many vector to quantize your data. Try to find the minimal distortion. So maybe easy way, just this coefficient, the distortion minimize. The other one, we can base on this quantize. Maybe this one best match this one. So we didn't know which one. So we can base on this one, recover according this covector. So we can recover back from the spectrum. Different covector have different envelope shape. Different have different envelope shape. According envelope shape, so different covector have different envelope shape. So we can base on envelope shape, try to match original signal waveform, and to see which one is minimal distortion. So you can see one is easy way is from the distortion, weighted distortion. So maybe I can use a simple one. So we have an LPC coefficient, LPC, to generate nice spectrum frequency. So we have an element like A0, A1, A2 up to the A10. So P order equal to 10. So according this kind of condition, we have to do the quantization. If we are doing the quantization, so you have to think about maybe we're using the covector, codebook. So we have a codebook here. So this one is maybe we just have a vector quantization. We are using vector quantization. So vector quantization. So you have a many vector. So you have a V1, V2, V3, so many vector. Each vector, like a V1, maybe we have a vector like a V10. So if we are trying to use a mean square error, try to do the best match. So if you are trying mean square error, so that one is a simple one. So you try to become the summation like a AI minus BI. So we take a square, summation there, distortion, I equal to 1 to 10. So we can maybe divide it by 10. So it's mean square error. So this one is your error function. If you are consider weighting mean square error. So maybe we can have put some weighting here, weighting coefficient here to try to emphasize some low frequency, low phase angle, or high frequency phase angle, depend on you. So most of them we are highlight low frequency, because night spectrum frequency, they have some frequency order. So they can be low frequency and high frequency. So most of them low frequency, the weighting value become bigger. Another one, so because if we know this one is our codebook, each codebook is corresponding maybe night spectrum frequency. So this one is like a V1 is our like a covector. So we can recover become a spectrum, because this one, because it's a nice quantized, is like a quantized nice spectrum frequency. So V1 is a quantized nice spectrum frequency. We can recover the corresponding LPC coefficient. So LPC coefficient is a quantized LPC coefficient. So based on this coefficient, we can cover their frequency response, their frequency envelope. We can, based on this coefficient, can generate frequency. Right now we have to do the quantization. During we are doing the quantization, so we can using the like a covector, like a vector matching. So maybe just an easy way, mean square error, or the other one is a weighted mean square error, or the other one we can base on each vector, so they can be represent the quantized night spectrum frequency. So based on quantized night spectrum frequency, we can recover like a quantized linear prediction coefficient. So based on this one, we can come out their envelope shape from the frequency domain. So we have an original signal. This one original signal also goes through FFT. So you can see many envelope harmonic here. So we can calculate the distortion. So we can base on like a spectrum distortion. So you can see this one is like a original speech signal. So S prime of W is from LPC night spectrum frequency. One is the original spectrum. This one S prime of W from your textbook. So you can see S prime of W is our quantized night spectrum frequency, recover quantized linear prediction coefficient and go back to their frequency response. So we can base on which one have minimal distortion. That one will be winner. So you have to say, well, we base on each covector. So this one we can construct it early because the covector is well defined. So they have a corresponding, this vector corresponding, maybe we are not stole the covector, we stole their envelope. We stole the S prime W1, like S prime W2, maybe we stole their many vector corresponding their spectrum envelope. So we can base on spectrum, original spectrum, to calculate distortion. And then once we quantize, this one index 0, index 1, so the minimal distortion, the index is our winner. Index is our compression data. Okay, so before we do quantization, we have to know how to calculate distortion. So one is based on spectrum, the other is the easy way, just night spectrum coefficient to calculate the distortion. Okay. So in speech processing, we are not only focused on because we try to see your performance. Sometimes we try to know your performance. Sometimes you have to know, so average spectrum distortion should be less than 1 dB, and then fewer the outlier at 2 dB should be percentage should be lower, and outlier 4 dB should be no outlier for 4 dB. What do they want to say here? So if we are consider textbook, we look at textbook here. So spectrum distortion, so they can be a good measurement because from the perceptual point of view, so from two set night spectrum frequency. So overall distortion caused by quantization scheme. So maybe you can use a simple one, spectrum distortion over a large sequence vector. So however, what's the performance we have to achieve? We hope to average spectrum distortion. So we have a many speech frame each speech frame find the best match covector corresponding spectrum. So that kind of distortion should be less than 1 dB, and then we hope an outlier, the speech frame number of speech frames should be smaller than 2%, 2% fewer than 2 dB. So right now is between 1 dB and 2 dB. They hope only 2% fewer than 2% outlier. So no outlier over 4 dB. So the meaning, because in speech signal during, so if you are signal like, for example, your signal is sine wave. For example, your signal is sine wave. And then our quantize is a perfect match. Our dequantize is a perfect match, almost perfect match. And then only one point is different. Only one point is different. So the black one is original signal. The red one is your dequantized. So we are dequantized signal. So maybe it's a decoded signal. Okay, so if you are decoded signal, every point is a perfect match original signal. Only one point is a very big difference. So this one is like this kind of signal at perceptual point of view is not feel comfortable, because that one is like an impulse response. So the human being will be affected by this impulse from the perceptual point of view. It's not good, you know. From perceptual point of view, it's not good. So if you recover signal, not a, let me check. If you recover signal, or maybe a little bit distortion, you know, it's not a perfect match. Like this one, maybe yellow one. I'm not sure you can see it or not. So if you are recover signal, oh, it's not a perfect match, you know. However, the shape is almost close. So the distortion is higher, because this one just only one impulse different. The other one is a perfect match. So that one is average distortion. Average distortion is lower, but 2 dB is okay. 2 dB below 2%. 2% is mean your speech frame, number of speech frame. 4 dB, well, you have one bigger than 4 dB. This one should be smaller than 2 dB and bigger than. So if you have one big noise here, that kind of recover signal from the speech point of view, human perceptual point of view, is not good. So it's not to see the average distortion. We have to see your reconstructed speech signal and make sure no big distortion come out. No, we do not allow big distortion. So big distortion is not allowed in compression. So average distortion sometimes just give you an indication. how perfect match original signal. So, but however, some point is a perfect match, but however, some point you have a big distortion. From the perceptual point of view, the big distortion is easily human being to catch that distortion. So make the quality, your speech quality would be not good. So we have to think about, so you can see here we are consider three criteria. First one is average distortion should be less than 1 dB. And also the outlier around the 2 dB, maybe some guy big close to 2 dB distortion cannot occupy too many. So maybe just below 2%. Below 2% of your speech frame, the distortion could be close to dB, but no speech frame distortion bigger than 4 dB, reach to 4 dB. So this one just for your idea. Why? Because they are from the perceptual point of view. Big noise, just 1 point, big difference. Human being will be sensitive. So sensitive this distortion. So I will tell you from the if we compare your ear and eye perception. So the ear perception sometimes is better than eye perception. You know why? Because your ear perception, sometimes one big difference, one point difference, 1 point signal point, your sound point, one point big difference, you'll be catch that point. But eye perception may be one noise, you maybe it's not easy for you to catch. You have to be big distortion, big difference. But the big difference depend on spatial resolution. Sometimes the spatial resolution, you are not easy to catch that point because the background is black and only white point in your black. But that spatial resolution is too small. You stand far away on that point, on that picture, so you cannot catch that white point. But if you are hear the signal, speech like sound, you can catch the sound pressure. But they have a big difference. You will catch that point. So you can see this one from the eye. You have a larger contrast difference. However, we have to consider how far the human being, the human related to the subject. If it's too far, it's not easy for you to catch that white point. So, however, if you can hear, but however you can see that picture. But here you catch the sound. If one sound is big difference, so you'll be catch a little bit difference. You can catch that one is not feel good. So in general, sometimes we can say your ear perception resolution is better than your eye resolution. So some guy will be comment like this one, but maybe you have a different point of view. It's not always rule. But I just tell you, the human being ear is sensitive, a very small point, big difference. So they can catch that point. Okay. So this one is like your weighty. However, some of the implementation they try to make sure reduce the computation complexity. So maybe they just using easy way, mean square error. So mean square error to do the calculation. So if you have a weighty, so like this one, so they just using like this kind of mean square error. So if you have a weighty value, so f is a nice spectrum frequency vector. So they're using like this one. So you can see they come out like this kind of equation. And then they will be considered how to do the weighting function. So because we are open model, and also we are considered like a Foreman, because LPC from the frequency domain, we are LPC filter coefficient. They are model our envelope shape, signal envelope shape. But signal envelope shape is more related to if we are trying to think about. Right now we are talking about weighting. We are not consider spectrum distortion. If we are consider minimal computation complexity, if we are using this approach, so your computation complexity will be lower compared with spectrum distortion calculation. So if we are compare spectrum, however, we have to, but the spectrum distortion calculation is more meaningful, useful for your perceptual point of view. So right now we are thinking about if we are using the simple way, so how to do the weighting mean square error. So and then we'll be talking about how to using the weighting coefficient here. So one guy proposed, if you are a low frequency here, so there's one like A. So we have a A1 because we know our nice spectrum frequency coefficient, they have a phase angle related. This one small phase angle, so it's 0 to pi or 0 to 2 pi. So they corresponding 0 to 4 kilohertz. So this one is a low frequency, and then from low frequency to high frequency. So this one they told you if the coefficient is lower, so the weighting function is 1.0. So it's A9 will be using a small value. This one will be using 0.8. This one will be using 0.4. The weighting function is 0.4. The other one will be using 1. So the guy told you if we are trying to using the weighting mean square error to do the quantization, so we can low frequency we can keep the original weighting value 1, and high frequency coefficient will be using 0.8 and 0.4. So you can see the other guy using different way. Then when they are consider neighboring coefficient relation. They consider the neighboring nice spectrum coefficient correlation, the distance. So if the distance they are very close, they using the top one. If the two nice spectrum frequency coefficient neighboring coefficient are bigger than 450 hertz. 450 hertz. Total will be 4,000 hertz. So 4,000 hertz. So if they're bigger than 4,000 hertz, they're using this weighting. So almost like a low frequency, we are using high weighting value, high frequency value. So if we are bigger space, using the bigger space, we are give them the low frequency. Small space, because neighboring frequency they are close, we give them the high weighting value. So you can see if you are more closely your neighboring, so Fn closely your low frequency, closely to your high frequency, your neighboring, so your weighting value becomes bigger. If you are far away, you are alone, you are not close to your neighbor coefficient, so that one your weighting value become smaller. So you can see they try to think about if we are coefficient more closely, so they look like you have a peak point over there. So this one is from different point of view. What do they want to do? So from this figure you can see the physical meaning. So okay, make it smaller. Okay. No. Okay, so you can see one is linear. This one is your linear prediction coefficient spectrum. So linear prediction coefficient spectrum. So we have to see this one is more like a night spectrum frequency location. So you calculate your night spectrum frequency coefficient. So this one is more like a like your original signal envelope shape here. So linear prediction spectrum here. So our night spectrum frequency location is more like here. First coefficient, second coefficient, and third coefficient, and so this one, first one, second one, third one, fourth one, fifth one. So you can see we have to highlight the peak point. So this one is your value. So we are now the weighting value becomes smaller, and then this one is your peak point. We try to highlight. So the other high frequency, the weighting value becomes smaller. So the main idea. So the main idea, because what's the LPC? You know, because we have a signal and partition to the speech frame. So speech frame from the frequency domain. So you can see we have many harmonic. So our short-term prediction LPC coefficient try to model your envelope shape. So according your model envelope shape, so we hope to your envelope shape be modeled better. So if we are looking into your night spectrum frequency like this figure, so we hope to, if your night spectrum frequency, why this envelope shape? Because envelope shape first peak point we call the Foreman 1, second peak point we call the Foreman 2, Foreman 3, and Foreman 4. Why we this one in our we call the Foreman. Foreman is related to your linguistic. So linguistic spectrum pair coefficient. So we can see once your frequency close to the peak point. So peak point. So this one, and this one, and this one. So will be highlighted, and the other one is the other coefficient we are not highlight. And make sure your peak will be preserved. Make sure your peak will be preserved. So make sure your peak will be preserved where? So will be preserved where? So will be make your quality better. So our nice LPC is a model. LPC is a model your speech signal envelope shape. So based on envelope shape, we can come out a four format. We have a four format. So this four format is related to your phonic understanding, like R, E, U, A, O, the basic sound understanding. So we have to make sure during our quantize and dequantize, and this peak point will be keep preserved where not big distortion occur on the peak point. So you can, if we find out our night spectrum coefficient close related to our first format, second format, third format, and fourth format, their weighting value will be give them the higher weighting value. The other, if we are related to vary, so that one weighting value will be lower. So the main idea, because our night spectrum frequency, we are quantizing LPC. LPC is related to your speech frame envelope shape. From the envelope shape, we know we have around format. So we try to model, make sure your format peak point will be kept where. So we try to, if your night spectrum frequency related to the peak point, will be given a high weighting value. If the night spectrum frequency coefficient related to the vary, so this one is your vary, this one is your peak point. So related to peak point, envelope shape peak point, so we have to give them the weight value, the weight bigger. And then if the relative vary, so is lower point, so we give them the weight value lower. So what they propose here, they try to guess. Most of them, they try to get a good perceptual point of view. Try to reduce, we are not perform spectrum distortion. Spectrum distortion will be take a lot of computation. Right now, we just only have a 10 coefficient. So to do the calculation, so that one will be easy. Okay, so I using the Mandarin to repeat it. 那我们既然要量化 LPC， 第一步要做的事情是，要去了解我到底怎么去算 distortion， 因为主要的精神这个，因为它是10个 element， 所以说呢 P 是等于10比较常用。它大概都是 vector quantization。那 vector quantization 的话，那你会遇到一个问题，怎么去算 distortion？ 那如果我的 quantization vector 里面的 component， 直接是 component 的误差，那就会出现了，就是算mean square error， 算 mean square error， 算这个 mean square error。那但是 mean square error 呢，每个系数的重要性不一样。那有时候我会要给 weighting value， 这叫 weighting mean square error， 也就是说到时候我算出来最 match 的那个 covector， 比较还原会比较好。那正常来说，我既然实际上LPC 实际上是有关于讯号的 envelope shape， 那我每一个量化的covector 都可以对应到一组，它原来应该在频谱的 envelope shape。那我只要去算什么呢？我干脆就是算 LPC 它的频谱 ，LPC 原来的频谱图，频谱应该 LPC 在时域轴原来的频谱，然后呢，我对应到的 night spectrum frequency 应该要的频谱图，我只要比这两个频谱谁比较像就 OK 了，误差最小。那每个频谱呢对应，那频谱要比对就很多点了要看你的 FFT 的点数，那这个相对就 就要加总，比这个10个点还来得多，那当然计算量就多了。那所以说呢，当然就会说，如果我考虑到对，另外一个呢是考虑因的特性。因的特性呢，我们在算并不是算平均误差除了平均误差之外，我们还要去看你的误差有没有从 spectrum distortion 的角度这是算 spectrum distortion。你的误差呢不能希望不要超过2% 的音框大于2 dB 的误差，那也不希望有4 dB 以上的误差。主要的原因，人的耳朵很 sensitive， 它是一个一维的讯号，但是呢，在这一维讯号突然有一个很大的突破，人会听得到。只要你听得到声音，那你就会听得到这个很大的巨响，就好比雷声离你很远，那你还是听得到这个雷声。但是这个影像离你很远，它是一个背景是黑的，突然有一个白点，很抱歉，你看不到它。好，所以说从某些角度来看，人的耳朵的 perception 是大于你的眼睛的 perception。就像打雷，你看得到，打雷你听得到声音，但是你说闪电你可以看得到，那闪电的那个值是很大的，闪电是很大的一面。但是呢，声音呢，如果你并不一定要雷声，只要很短的时间有一个突破，人是听得到。那闪电呢，实际上它占的面积够大，它不是一个点。如果是一个点，人是正常来是听得到，但是呢，如果是一个点在一个面上，人要发现它，跟你的spatial resolution 有关那所以说这是我们在看音的品质的效果的考量。那另外一个呢是那既然计算量那么大，如果回到 weighting mean square error， 那怎么去做？那 weighting 呢，到底要针对这10个系数怎么 weighting？ 那一般来说低频比较重要，高频相对会比较没有那么重要但是呢，大部分都会考虑我的那个 night spectrum frequency 接近什么？接近我的那个因为我们实际上 LPC 是在做什么事？ LPC 就是一个 short term prediction。 那 short term prediction 呢，实际上是抓什么？抓你的频谱的 envelope share。 为什么呢？ envelope share 的波峰，为什么？因为我们是 OPPO model， 所以 OPPO model 呢 model 你的频谱讯号的波峰效果好，波谷效果不好。那既然是抓 envelope share，envelope share 又从语言学里面呢跟你的是代表 phoneme 1、phoneme 2、phoneme 3、phoneme 4不同的音 R-E-V-L-O， 它的音这些 phoneme 1、phoneme 2、phoneme 3、phoneme 4所在的那个位置不太一样，男女生当然有别。所以说每个人在讲他的音呢，你大概都听得出来，因为他嘴巴从小到大嘴巴要怎么发，嘴巴要怎么发，那所以说相对的每个人发音的口腔被设计的都一样，都接近要一致性。那一致性的话，所以说我们当初 Source Filter Model 就按照你的口腔是一个声学导管的概念去建构。那我既然 model 波峰比较好，那我希望我的那 night spectrum frequency 比较有关我的频谱的波峰点 LPC 的波峰点那个地方的 weighting 要大。所以说呢，他们就找但是呢，你如何在你的 night spectrum frequency 里面去找到这些系数是接近波峰？那实际上最笨的方法就是2个 night spectrum frequency 靠近的时候，实际上是接近波峰，那相邻的差很远，那就可能是波谷他利用这种概念不管用什么方式想办法去抓到波峰呢，突然就会加 weighting 会变大，那波谷呢就相对就不需要，这边是没有 night spectrum， 那这边呢就慢慢就降下来。所以说你可以看它的 weighting 呢是根据你的 envelope share 去做 weighting 这样的话效果会好从 perceptual point of view 相对效果好。 Okay, so right now what we figure out, one is a night spectrum frequency, And second one, we are trying to do the quantization. First issue, we have to figure out how to calculate distortion. So we have a basic idea is mean square error, and the other one is weighted mean square error. And also we are consider how to do the weighting. So weighting value, if a night spectrum frequency coefficient close to envelope, close to your Foreman location, so we are trying to keep the weighting value bigger. And if we are close to not close to Foreman, just close to a valley, the lower point, so your night spectrum frequency coefficient, the weighting value becomes smaller. So the main idea is like this one. Okay, so once we have nice how to calculate distortion, and then we are consider how to design the quantization codebook. So you can see we have a 10 coefficient, so typical required, so you can see only 20 to 25 bit. We have a 10 coefficient, so you can see 10 coefficient we only can use around the 20 and 25 bit to quantize our night spectrum coefficient. And then also we hope to get a good performance, good accuracy. So you can see that one we have to think about how to make the quantization efficiency higher. So sometimes they have a two approach. One is split vector quantization, SVQ. The other one is a multi-stage vector quantization. It's not a one stage. Why? Because one split vector quantization, because we have A1, A2, maybe I use a different one. So we have a sorry. We have a night spectrum frequency. We have a A1, A2, A3, A4, 5, 6, A7, A9, A10. So first one we call the split SVQ. So split vector quantization. So this one they call the split vector quantization. So we can partition to many subvector. So this one is a 3 subvector, and 4 subvector. It's not a big subvector. This one is your subvector. So each subvector they have a corresponding codebook. Is codebook 1, is codebook 2. So codebook 1, codebook 2, and then this one have a codebook 3. So based on your each codebook, so they are do the vector quantization. So right now we are using around the 20 to 25 bit. So each codebook can be 8 bit codebook. So is 8 bit codebook is around how many covector? So we have a 256 covector to do the vector matching. So this one is 256 covector. So if you have a night spectrum frequency, we are using split vector quantization. We are partition many subvector. For example, we partition 3 subvector. It's not dividable, so we are 3, 3, 4. And each subvector have corresponding codebook here. So they have a low frequency codebook 1, middle frequency codebook 2, and a high frequency subvector codebook 3. So each codebook, so your complexity will be easy. So another one they call the multi-stage. So it's called a multi-stage. Multi-stage vector quantization. So multi-stage vector quantization. So we have we can use in the three-stage codebook. So this one is your vector. So there will be like a AB codebook. AB codebook here. Do the quantization, and then you have a distortion. You'll be second codebook. You have a second codebook. So you have an index come out, index 1, and then if you have a distortion, you have a maybe difference. So you have a best match. So you have a difference vector. So this one is your difference vector. Best match difference vector. So you have another AB codebook here. So codebook 1, codebook 2, and then you also have a difference vector. So and third one, you have an AB codebook here, AB codebook 3. So you have an index 1, index 2, and index 3. So this one is a multi-stage. So multi-stage vector quantization. So multi-stage because we are using 24-bit. So we are trying to think about first one we are quantized around your mean. This one could be your difference, quantize your deviation, and this one is quantize your second order deviation. So you can see if we are trying to have a best match covector, will be calculate the distance differentiation. We are a best match, we calculate the difference factor. So we using the difference vector go to the second covector search and try to find the best difference vector and try to find the second order difference vector. Later on you have a first like a mean difference vector and second order difference vector will be combined then together, will be reconstruct your original signal. So this one is a multi-stage vector quantization. So you will be say why you do not using one covector 24-bit codebook. 24-bit is 2 power 24 covector is too big subvector. So however, here you can see multi-stage vector quantization. Usually the performance better than split vector codebook. Because why? Usually multiple stage vector quantization, the performance bigger than split vector quantization, because split vector quantization can view is could be is like a spatial event. They could be considered. We can, if we are considered like this one. So first one we can quantize our covector. Only 3 subvector have value. The other one is 0. And this one only middle have a value. The other one is 0. And this one is the last 4 have value. The other one is 0. So you can see if we are multiple stage vector quantization, we are design your codebook. Suppose be their covector is have 10 elements. So we are assume only in front of 3 elements have value. The other is 0. And second covector, we are assume in the middle we have a value. The other 2 part middle frequency 3 component we have a value. The other is 0. And this one we can assume the last 4 components have value. The other 6 component is 0. So you can see our multiple stage vector quantization become SVQ. Under this kind of arrangement, design your codebook. So this one become SVQ. However, multiple stage vector quantization, this part may not be 0. So you can see multiple stage vector quantization cover split vector quantization. So the diversity, this one diversity is bigger than split. The diversity will be bigger than maybe we can call variation. So variation will be bigger than split vector quantization. So so the performance used to be multiple stage vector quantization will be better than split vector quantization. However, the complexity, this one is higher because the cobalt vector match is 10, each covector is 10 element. So your calculation is 10 element. For this one, split vector quantization, first cobalt only three element to do the subvector matching, and second one only three element subvector matching. So this one is a 4 element. But the multiple stage, each cobalt using the 10 element, the vector is 10 element to do the covector matching. Try to find the best match. So used to multiple stage is supposed to be multiple stage vector quantization. Complexity is higher, but the performance is better than split vector quantization. The reason is multiple stage vector quantization, they have many variation that cover split vector quantization. So we are not using one codebook because if we are using 24-bit codebook design, the complexity is, if we are trying to do the covector match, it's impossible. It's too many, and also it's not easy to design. It's not easy. Come out your codebook, because come out the good codebook. So it's too complicated. So we are considered more like some hierarchical the vector covector design here. So split vector quantization become original vector is partition many subvector. According subvector, they are do the quantization. Okay, so here they have some example here. So if we have 2 subvector is a 5, 5, 3 subvector would be 3, 3, 4, and 4 subvector they can be 3, 2, 2, 3. So they will be show you the complexity. So the subvector, if you are partition more, so the complexity become the lower, and also storage, because your codebook storage could be also lower, and also the bit arrangement could be almost the same. But the performance, if you give many split, the performance become lower. Okay, so there are several drawbacks related to your split vector quantization. So correlation between subvector not exploit. Why? You know, according our night spectrum frequency, all the coefficients they have some order, because this one frequency is higher. They have some order. Frequency will be A10 will be higher frequency than A9, A8, A7. So you have some correlation here. If you are partition become many subvector. So this one like a subvector relationship between is not connected. So correlation. So this one we call the blocking effect. So this one will become out your blocking effect here. So correlation between subvector are not well discussed, well addressed. So also only a fraction intra-frame correlation is used. So a pair night spectrum frequency close to peak may not be split to different subvector. So maybe we are trying to say this A3, A4 related to your envelope shape peak point. so they have to give them the bigger weighting value, but they become a different subvector. Sometimes during the quantization, they try to best match the covector biased by A1 and A2. So would be affecting A3 and A4. They should be have a high impact for your make sure they are not have big distortion because they are related to the former envelope shape peak point. So you can see sometimes the peak in the spectrum may be split into two different subvectors. So they have some correlation. They have to quantize independent. So this one quantization efficiency will be decreased. So once your subvector size become reduced, become so small, so you have partition too many subvector, so your quantization efficiency will be decreased. So some combination subvector maybe will be considered respect the ordering on night spectrum frequency, so will be come out to your neighboring night spectrum maybe too close to each other, because this subvector will be quantized by himself, this subvector will be quantized by different code book, and maybe this after during the quantization this one move higher, move bigger value, A4 become the smaller value. Sometimes the order will be changed, so will be cause trouble. So the minimal spacing limit you'll be allowed, so you have to be double check. Do they make sure they keep the minimal spacing? So in the standard 3.723.1, they have a minimal spacing check. Make sure they did not change the order. Minimal distance. So make sure they keep the minimal distance. So number of bits allocated to each subvector is fixed. So if a weighting function will be limited within the one subvector, so a vector only on night spectrum is relatively small important. Some subvector is not important. We cannot move the bit to the other subvector because AB here, maybe high frequency in this content is not so critical issue, or maybe they're using 7-bit here, maybe they're using the 8-bit here, this one they're using a 9-bit, can get a good performance. However, we already fixed it, so we are not according your content perceptual point of view to relocate your important part. So the weighting function will be limited in one subvector. So sometimes the performance of split vector quantization maybe is not can come out a good performance. So multiple stage vector quantization, you can see your quantized night spectrum frequency. So will be based on many quantization vector combined. So we will combine this one. So this one is look like we quantize their mean, quantize the difference, and second order deviation. So during the decoder, this covector and this covector and this covector will be combined then together. So we'll be combine this covector and covector. So you can see the combine first covector and second covector and third and so on, combine them together depend on how many partition. So multiple stage split vector quantization can treat a spatial event like a multiple stage vector quantization. Why? You can see we are first one, we are only focus two elements, the other element is 0, we design the codebook. And second codebook, we are also focused on this two, and the other is 0. So your multiple stage vector quantization become a split vector quantization. So you can see they have performance at least equivalent to that. So sometimes they will be much higher. So typical multiple stage 5, 6 and male capture encoder mixed excited, they are using the multiple stage vector quantization. So this one is a multiple stage vector quantization. If we are partition many stage, so we'll be make your each code book bit number become smaller. So you can see there. Sometimes you try to search your multiple stage, so you have to think about also put a weighting value here. So we have a signal combine, try to match different depend on which stage here. So you can see this one is the first stage, first code book, we try to do the match, and later on will be second code book. So however, how to do the search? So best search, sometimes we can say, well, is sequential. This one is look like a sequential search. First one we find the best match to come out the difference, and then difference vector do the second search and find the best match, and also find the difference vector and also do the search. This one is sequential. Also, you can consider could we search them together? This one, if we have a two code book, could we search together? Well, if we are search together, complexity will be higher, because if we are first one, select one, and second one, so your complex supposed to be this one complexity. If we are sequential search, like a covector, covector search. So your complexity, first code book, second code book, and third code book. So you can see your first code book you have a 256 covector search. Second code book is 256 search, and third code book will be 256 search. If you are consider three code book search together, so your complexity will be higher, because this one is 2 power a, this one 2 power a, this one 2 power a. So if we are from the code book 1, we pick one, there will be here we pick one, and then this one we have a 256 combination, and then this one is 2, so you have a 256 combination. So you can see here, so you'll be how many you have, so you'll be plus and plus so on. So total code book search combination will be 2, so many, say 2 power 24. So you have so many code books, code vector search. In the past, we just this one code vector search like this one. So if we are trying to combine them together, the code book search is so complicated. Like this one, it's not a look at a sequential. It's try to consider multiple code book together, try to find the best match. And then you have to combine many. So that one will be more complicated. However, maybe we can the other one make your because sometimes first one is the best match. But second one is the best match. It's sequential, but the total maybe is not low distortion. Maybe our first one take a second best, and third one will be second best, and final will be best one. Combine them together, total distortion will be lower. So right now they say, well, we can do minimize. So first one is not only one winner. We are trying to think about maybe m best. First one we try to find like this figure. So you can see first step is not a try to find only one winner. We try to find two winners according to winner. So you can see will be multiple. You have a match 256 for example. so 256. So you can see, and second one, during the second stage, also we try to select a 2 winner, and then later on we try to best match. So you can see, according to this one, finally we are compared these two paths. Which one is total distortion would be lower? So that one could be improve the performance. However, it's not a full search. So we are in each stage we are trying to find M best. So that one can minimize some distortion. Why this one is good? Because this one can minimize some distortion, some computation complexity, also can get sometimes a performance improvement, better than sequential search. So that one is what we say, you can get a little bit improved performance. So sequential optimization maybe is not provide the best performance. So the last stage, so better alternative maybe iterative sequential optimization. Sometimes you can do the iterative, but however maybe you can use in the MBES. And this one is couple training. Is not we not touch that one. So MBES sometimes will be get a better performance. So you can see first couple we select the M covector our winner is not the only one winner, and also go to the second codebook. We also try to find N winner. So that one, so we can find the best one. Okay, another issue is couple training. So basic couple training usually is single stage. You can base on single stage sequential optimization. So you can say how to do the couple design. Before we say that maybe like a k-mean method. So k-mean method is based on your input vector. So we can using the k-mean method try to find the best covector, sometimes the local minima best covector, and then we are original training data based on your covector. You can get a difference vector pool, difference vector set. So difference vector set, you design the your second codebook, and also according your second codebook best match. Also you can calculate your second order difference vector and different vector group set. So according that kind of difference second order difference vector, we design the codebook using the k-mean. So this one is like a sequential design. So is sequential optimization. But however, sometimes this kind of codebook design maybe it's not good. So maybe you can consider iterating. So you can see we are all the finish. So we can consider provide better alternate iterative sequential optimization. When initial codebook is chosen for each stage, each codebook is then optimized by assume all other stages to be fixed. So first time is sequential, and second time we are consider the other two is a fix. So you can see here we try to do the vector matching grouping and combine the other fixed covector to do the best match this one. So you try to re-optimize this codebook, and later on this one fix, try to re-optimize this codebook here. So they call this one is like a iterative optimization. So also you can consider all codebook simultaneously join codebook design, but this one will be could be get a little bit better performance, but the computation complexity is higher. However, you can consider three covector design together simultaneously. Well, that one is a high computation complexity. It's not easy. Used to be could be sequential design. Later on, these two covectors are fixed, and then we redesign this one. So input vector, try to do the grouping according your first codebook, and try to do the grouping, and also consider MBES. consider embed, try to reorganize which group is best, and then try to reoptimize this one. And later on, this one fixed, and then we can generate consider this one, the other two fixed, and then try to optimize this one. Try to do the grouping again and centroid again according the other two fixed. However, if you are trying to consider 3 code book designed together, it's okay, but it will be take time because they have a many combination. Try to do the grouping, clustering, so you'll be take time here. Take a lot of computation complexity to find the best relative good code book come out. Okay, so right now what we're talking about here, they try to quantize your night spectrum frequency. So they already almost like here they just talking about split vector quantization, multiple stage vector quantization. So just 2 examples for you. Okay, I use the Mandarin. Okay, repeat what I talking about this section. 那接下来呢，我们要看的是量化所以量化最常看到的结构呢有2个，因为我们的 vector 是10个 element， 所以有点多。那所以说呢，一般来说 night spectrum frequency 大概量化是20到25个 bit。你有10个元素，每个元素16 bit 的话，你就大概是切成多层次第一次是量化它的 mean， 第二次是量化它的差值，再来是第二阶的差值。那这样来做，那代表每一阶呢可能都8 bit。那一般来说 multiple stage vector quantization 是 cover split vector quantization 那其次的话因为你都是 sequential， 那split vector quantization 有一些问题，因为它的原来这些 coefficient 有 intra-correlation， 你把它切开来就会造成有一些 blocking effect。那另外一个 boundary 呢，有时候在量化的时候 A3 呢可能变大， A4 可能变小，它本来有一个frequency different 的区间，这个可能要确认，否则会有稳定度的问题。那其次的话其次考虑到你的 covector 的 search也就是说我如果 sequential 的 search subvector split vector quantization 没有这个问题就是每个对应的code book就各自去做配对。那如果你是 multiple stage vector quantization 有一个问题，第一个code book呢如果是最 best match 的话，那剩下的差值到这边做配对的时候，有的时候可能第一个code book选第二个 winner， 接下来配对的结果可能会是整体失真最少，所以说它才会 come out 有 n best 就是每一集呢可能选2个，选3个 winner， 再到下一集呢再找3个 winner， 最后整体来看谁的误差最少，这就是 n best。那不太可能把3个code book一起来做搜寻，一起同时做搜寻，它的复杂度就很高了因为它的组合就2的24次方，那这根本就搜寻不完n best 当然复杂度增加，但是相对增加不会那么多那最后呢它有 comment 怎么去产生这个 code book 那也就是说你可以用 k-mean 的方法，那一个一个来做第一，也就是做完这个可以产生你的 difference vector， 从原来的 training data， 那再做一步做，也可以说 iterative 就是重复性，2个全部做完之后，这2个固定，那这个重新再做配对的时候，同时你要考虑你的误差，从这2个固定的 code vector 去再做配对一次，整体的那个最小的误差才是配对，也就是说因为你在 grouping 的时候要考虑这2个 covector， 所以说会影响到你 grouping 的那个配对的 covector， 那重新再 optimize， 那当然也可以3个一起 optimize。 OK， so right now we almost finished talking about the today what we talk is talking about from the what's the Paco physical meaning. And later on, we're talking about how to Paco coefficient, how to generate nice spectrum frequency. They are from the particle structure, so it's related to your vocal tract. So and then right now, and then we are thinking about nice spectrum frequency. They have an intra-frame and inter-frame correlation. So we know that their characteristic, and later on we are thinking about how to quantize. So we are propose here, we are split vector quantization and multiple stage vector quantization. And then we are talking about multiple stage vector quantization is cover split vector quantization. So however, computation complexity is higher. So that's why we stop here, and we'll be talk to you next week online. And also don't forget our final exam it will be June 23rd. So will be 1 week, 2 weeks, 3 weeks, will be 3 weeks later. And also in this week I will be give you the homework 2 guideline, so you have to consider how to implement sound localization. And also TA will be help you to generate the testing sound. So we'll be give you some configuration. Sometimes you can request send a message to the TA, ask him to help you to generate the the sound for you to determine the sound localization for your program. So right now that's it. So talk to you next time. Okay, thank you, bye bye.